Hey, in this video, we're going to be talking about rotational kinematics. Just like we did in Unit 1, the kinematics process, what are the problem-solving steps? It's going to look a lot like what we did in Unit 1, so take a look at this lesson and example. So now let's get into rotational kinematics, all right? And so one of the things you got to recognize is there's a correspondence between the rotational motion variables and the linear motion variables. And last time we talked about the angular displacement corresponding to the displacement. Angular velocity is given by this Greek letter omega, and that compares to velocity. And omega is again defined just like linear velocity was defined as the displacement over the time, right? Angular velocity is the angular displacement over the time, that rate there. Angular acceleration is the rate of change of the angular velocity. And remember, these are like averages. This is average. We use the derivative for those AP Physics C or for calculus, or that slope of that tangent line when we're doing the instantaneous value. And this is the angular acceleration. This is the Greek letter alpha. And linear acceleration is the change in velocity over that time. So that's kind of like the core variables, and they have an analogous part. Now, there's a connection between the distance, speed, and tangential acceleration of the angular variables, and let me tell you what we mean by that. So, and just because a lot of people can get confused on this, suppose I have something that's spinning, and I have like a piece of object here, and it's rotating from here to here. Okay, so it's going from there to there, and I want to know a few things. I want to know what this distance traveled. We'll call this S as the distance traveled. I might want to know how fast I'm moving, and let's assume the angular velocity is constant. So this is it's rotating this way, and the angular velocity is, say, constant. And angular velocity, again, based on this, is going to be radians per second. And there's a reason we use radians, and let me explain that to you. So I want to do a review of pre-calculus a little bit. So if I asked you, okay, from here to here, and I ask you, like, and let's call this distance r, the distance from there to there, and I ask you, oh, how does the angular displacement here relate to that distance that we travel? Because I'm going to travel, this object, this piece right here is going to travel a certain distance. And you have to remember this from your pre-calculus. You should have been taught this in pre-calculus. Some people are not. I'm going to just get rid of the change and just call this theta here. The arc length here, there's an arc length formula, and this is why we do it in radians. The arc length formula is the distance here is just simply r times theta. Okay, it's the radius times this angular displacement. That gives you the distance traveled. Okay, and I'm going to use the letter d because you might confuse that with speed, so let's just change those to d's. Doesn't really matter. I'm just saying the distance traveled is r times theta. That's the distance. That's that arc length of that circle there. Okay. Now, the rate of change, like the speed, is our distance divided by time, right? And this is the speed. This is the tangential speed that we're kind of moving at here. The distance is going to be r theta over t. And that theta over t, we write it as angular velocity. Okay? So the speed, this v here, by the way, is speed, not velocity as a vector. It's just the speed. The direction is changing because we're moving in a circular path. But the speed, the magnitude of the velocity, is going to be omega times r. That's where this comes from. And a similar thing for the linear acceleration, the tangential acceleration. If it is speeding up or slowing down, the tangential acceleration, not the centripetal acceleration. Be very careful. This is not the centripetal acceleration, which is different. Okay, the centripetal acceleration is the acceleration vector that's pointing towards the center of the circle, right? Perpendicular to the velocity. We're talking about whether it's speeding up or slowing down, the tangential acceleration compared to that, okay? So just be very careful, that's tangential acceleration. But we have these kind of correspondence between them, which we might use in some problems. So let's kind of go through like the process here. So, or just connect them a little bit. So constant angular acceleration. So just like in Unit 1, if the linear acceleration was constant, we can use our kinematic equations. And so the similar thing here, if the angular acceleration is constant, right, then we can use our kinematic equations. And we have a corresponding variables. We just switch the letters, right? And it's the exact same. Time doesn't change. There's no angular form of time because that's just a scalar. But we have the exact same equations we have here. This equation looks like this one, v naught t plus 1/2 at squared. So you don't have to memorize new equations. Like, they are the same equations. This is just v equals v naught plus at. So if you've memorized your kinematic equations, which I encourage you to do, then you have the angular ones. This one's v squared equals v naught squared plus 2a delta x. And again, it's just the analogous version of them. And here, this is the 1/2 v plus v naught times t. Right? Those are our 4 kinematic equations we can use. And so there's 4 rotational forms of those kinematic equations. So our problem solving steps gonna be really simple. There's no 2D rotational kinematics, so it's all just 1D stuff for the most part, but we're just gonna use the rotational forms. We're just gonna list out the variables, assign positive, negative directions to clockwise and counterclockwise, fill in the known values, identify the value you're looking for, apply the correct kinematic equation that relates the known values and the value you're looking for, and sometimes we may need to use the tangential. This is an extra step in here. We may need to relate the linear motion variables to the rotation if we talk about speed or distance traveled or the tangential acceleration. Not very common to ask this one, but in case you need them, those things are there. Some additional tips in terms of units. Normally, we're talking about angles in radians, but 1 revolution is going around the circle once, which is 2 pi radians. So 1 revolution is equivalent to 2 pi radians. You may need to use a unit conversion for that. So when we look at revolutions per minute, it's an angular velocity with different units. So revolutions per minute can be converted into radians, a measure of angle, and instead of minutes, you can use seconds there, radians per second. So RPM stands for revolutions per minute. If you see that, it's just another units of angular velocity. I generally will convert always into SI units. So if I see revolutions, I will convert it to radians. If I see minutes, I will convert to seconds, just like we normally do if you handle problems with different units. Okay, so let's take a look at this one. So with an 8 of a string, a gyroscope is accelerated from rest to 32 radians per second in 0.4 seconds. What is its angular acceleration? So we're going to list out our 5 kinematic variables. We're basically going to say, oh, we start at rest. We're going to go to 32 radians per second. We want to know the angular acceleration, and the time is 0.4 seconds. So what kinematic equation relates those? Is going to be this kinematic equation. Oops. T. So it's going to be 32 is equal to 0 plus alpha times 0.4. So then alpha is going to be 32 divided by 0.4, and we will get 80. And that's going to be radians per second squared. Instead of meters, it's radians. That's acceleration. How many revolutions does it go through in the process? Well, that one they're asking me about this variable now, right? Because this will tell me the number of radians. And so what kinematic equation can we use for that? We can use any of them because we now know that this is 80. I'm just going to use this one, but you can use it as an exercise to see if the other one should give you the same variable, the same value. So this is going to be 32 plus 0 times 0.4, right? Just plugging in the numbers. So it's going to be 16 times 0.4. That's going to be 6.4, and careful, our units are radians. But we want to convert it to revolutions, and we do our dimensional analysis for that. We say, oh, we have revolutions on numerator, radians on top. We know 1 revolution is 2 pi radians. So we're going to multiply this so the radians cancel. So that means I'm going to divide by 2 pi. I get about 1.02 revolutions, like that. Okay, suppose a piece of dust finds itself on a CD. CD is a spinning disk, compact disk, in case you need to know. If it's spinning at a constant rate of 500 revolutions per minute, right? That's what the RPM is. And the piece of dust is 4.3 centimeters from the center. So here's the center, and we're talking about this distance here as being 4.3 centimeters. What's the total distance traveled by the dust in 3 minutes? Ignore the accelerations to get the CD rotating. Okay, so let's look at the angular values, right? Because we're just find these things in angular values. The angular acceleration is 0 in this case. And we want to convert to radians, and we want to know the angular displacement. Because remember, if I want the total distance traveled, I can use that distance as r times the angular displacement. So if I know the angular displacement, then I can then figure this out. The initial angular velocity, we got to convert this into radians per second. So I want radians on the numerator and revolutions on bottom. And that will cancel that. And I also want minutes on the numerator and seconds on the bottom. So the minutes will cancel. I know 2 pi radians is 1 revolution. I know 1 minute is 60 seconds. So then I can multiply those out. So 500 times 2 pi divided by 60 is going to be 52.36 radians per second. So then that's going to be 52.36. and the time is 3 minutes. This is 3 minutes. We want to multiply by 60 to convert it into seconds because I want everything in SI units. So what kinematic equation relates those things is just going to be this one here, equals omega naught times t plus 1/2 at alpha t squared. But the angular acceleration is 0. So then we can just calculate this by multiplying 52.36 times 180. And that's going to be 9424.8 radians. And then we say, oh, but the distance we just multiply by 0.043 meters times the 9424.8 radians. Radians. And then times 0.043, and I end up getting 405.3 meters. Now, you might be a little confused, be like, hey, what happened to the units? It did meters times radians. Radians is technically a dimensionless unit, or it gets canceled out based on the formula. Based on this formula, so technically the radians go away. So a lot of people just ignore the radians. Technically, the reason this formula works is because like the radians get canceled out because you're dividing by 2 pi and it cancels out the 2 pi. I won't get into the math behind it, but just as a shortcut, we just say the radians doesn't really matter. Once you convert it to linear motion, the radians will get canceled out. So that's pretty far that it travels. If you found this video helpful, come check out our school community. It's got an amazing bunch of features. It's got extra videos, corrected videos, better than the ones that I have errors on YouTube. It's got multiple choice free response questions. I hold live Q&A sessions and go through more problems and I answer students' questions, help with schoolwork, all kinds of things. If you want to check it out, look in the description below or check out the website and find us in the school community. You get a 7-day free trial to give it a shot, just to check it out, see what it's like, come join some calls, and honestly, come learn AP Physics 1 even faster with us.